Hello class. In this lecture, we will learn about vehicle fundamentals. The figure on the left shows the forces acting on a vehicle moving up a grade. The tractive effort Ft in the contact area between the tires of the driven wheels and the road surface propels the vehicle forward. It is produced by the power plant torque and is transferred through transmission and final drive to the drive wheels. While the vehicle is moving, there is resistance that tries to stop its movement. The resistance usually includes tire rolling resistance, aerodynamic drag, and uphill resistance. According to Newton's second law, vehicle acceleration can be written as dv by dt is equal to summation of ft minus summation of ftr divided by delta mv, where v equal to vehicle speed. Summation of ft is the total tractive effort of the vehicle. Summation ftr is the total resistance. mv is the total mass of the vehicle, and delta is the mass factor. It is an effect of the rotating components of the powertrain. This equation indicates that speed and acceleration depend on tractive effort, resistance, and vehicle mass. As shown in the figure, vehicle resistance opposing its movement includes rolling resistance of the tires, appearing as rolling resistance torque TRF and TRR as shown over here, TRF and TRR, aerodynamic drag FW, and grading resistance MVG sin alpha. The roaring resistance of tires on hard surfaces is due to hysteresis in the tire material. In this figure, a tire at standstill is shown. On this tire, a force capital P is acting at its center. The pressure in the contact area between the tire and the ground is distributed symmetrically to the center line, and the resultant reaction force Pz is aligned along P. The deformation Z versus the load P in the loading and unloading process is shown in this figure. From this figure, it can be seen that due to hysteresis, the force P for the same deformation Z of the tire material at loading is greater than that during unloading. Hence, the hysteresis causes an asymmetrical distribution of the ground reaction forces. The rolling resistance of tires on hard surfaces is primarily caused by hysteresis in tire materials. This is due to the deflection of the carcass while the tire is rolling. The hysteresis causes an asymmetric distribution of ground reaction forces. The pressure in the leading half of the contact area is larger than the trailing half. This phenomena results in the ground reaction force shifting forward. This forwardly shifted ground reaction force with the normal load acting on the wheel center creates a moment that opposes the rolling of the wheel. On soft surfaces, The rolling resistance is primarily caused by deformation of the ground surface as shown in figure. The ground reaction force almost completely shifts to the leading half. The moment produced by the forward shift of the resultant ground reaction force is called the rolling resistance moment as shown in figure, and it can be expressed as Tr is equal to P into A. To keep the wheel rolling, a force F acting on the center of the wheels is required to balance this rolling resistance moment. This force is expressed as F is equal to Tr upon Rd, where Rd is the dynamic resistance of the wheel. Substituting Tr equal to P into A over here and replacing A upon Rd by Fr, where Rd is the effective radius of the wheel and Fr equal to A upon Rd is the rolling resistance coefficient. In this way, the rolling resistance moment can be replaced equivalently by a horizontal force acting along the wheel center in the direction opposite to the movement of the wheel. This equivalent force is called rolling resistance with a magnitude of Fr equal to P into Fr, where P is the normal load acting on the center of the rolling wheel. When a vehicle is operated on a slope road, the normal load P should be replaced by the component which is perpendicular to the road surface, that is Fr equal to P cos alpha into Fr, that is P Fr cos alpha. The rolling resistance coefficient Fr is a function of the tire materials, tire structure, tire temperature, tire inflation pressure, tread geometry, road roughness, road material, and the presence or absence of liquids on the road. The typical values of rolling resistance coefficients on various roads are given in table below. For car tires on concrete or asphalt, the rolling resistance coefficient is 0.013. For car tires on rolled gravel, rolling resistance is 0.02. For car tires on tar macadam, it is 0.025. For an unpaved road, it is 0.05. For a field, it is 0.1 to 0.35. Truck tires on concrete or asphalt, rolling resistance coefficient is 0.006 to 0.01. For wheels on rail, the rolling resistance coefficient is 0.001 to 0.002. The values for rolling resistance coefficient do not take into account their variations with speed. The rolling resistance coefficient of passenger cars on concrete roads may be calculated from the following empirical relation. Fr equal to F0 plus Fs into V upon 100 raised to 2.5, where V is the vehicle speed in km per hour. In vehicle performance calculation, it is sufficient to consider the rolling resistance coefficient as a linear function of speed. For the most common range of inflation pressure, the following equation can be used for a passenger car on concrete road. Fr equal to 0.01 into 1 plus V upon 100. Next, we will see aerodynamic drag. A vehicle traveling at a particular speed in air encounters a force resisting its motion. This force is referred to as aerodynamic drag. It mainly results from two components, shape drag and skin friction. The forward motion of the vehicle pushes the air in front of it. However, the air cannot instantaneously move out of the way of the vehicle and its pressure is thus increased as shown over here. In addition, air behind the vehicle cannot instantaneously fill the space left by the forward motion of the vehicle. This creates a zone of low pressure air. The motion therefore created two zones of pressure that oppose the motion of the vehicle by pushing it forward, high pressure in front, and by pulling it backwards, low pressure at the back, as shown in the figure. The resulting force on the vehicle is shape drag. Next, we will see skin friction. The air close to the skin of the vehicle moves at almost the same speed as that of the vehicle, while air far away from the vehicle remains still. In between, air molecules move at a wide range of speed. The difference in speed between the two air molecules produces a friction that results in the second component of aerodynamic drag called skin friction. Aerodynamic drag is a function of vehicle speed capital V, vehicle frontal area AF, shape of the vehicle, and air density rho. Aerodynamic drag is expressed as Fw equal to half rho AF CD V plus Vw the whole square. CD equal to aerodynamic drag coefficient that characterizes the shape of the vehicle. Vw equal to component of wind speed on the vehicle's moving direction. This component has a positive sign when this component is opposite to the vehicle speed and a negative sign when it is in the same direction as the vehicle speed. Aerodynamic drag coefficients for a few vehicles are shown over here. For an open convertible, the aerodynamic drag coefficient is 0.5 to 0.7. For a van type body, it is 0.5 to 0.7. For a ponton body, it is 0.4 to 0.55. For a wedge-shaped body, headlamps and bumpers are integrated into the body, covered underbody, optimized cooling airflow. It is 0.3 to 0.4. Headlamp and all the wheels in the body are covered in the underbody, then the aerodynamic resistance is 0.2 to 0.25. For a K-shaped small breakaway section, it is 0.23, and for an optimum streamlined design, it is 0.15 to 0.20. For trucks and road trains, it is 0.8 to 1.5. For buses, it is 0.6 to 0.7. For streamlined buses, it is 0.3 to 0.4. And for motorcycles, it is 0.6 to 0.7. The grading resistance from figure can be expressed as Fg is equal to mvg sine alpha. To simplify the calculation, the road angle alpha is usually replaced by grade value when the road angle is small. As shown in figure, the grade is defined as I equal to h upon L, I is equal to h upon L, that is equal to tan alpha, which is approximately equal to sine alpha. In some literature, the tire rolling resistance and grading resistance together are called road resistance, which is expressed as FRD is equal to FF plus FG. FF is given by mvg FR cos alpha and Fg is given by mvg sin alpha. Simplifying this expression, we get mvg into FR cos alpha plus sin alpha. When the road angle is small, the road resistance can be simplified as FRD equal to FF plus FG, that is equal to mvg into Fr plus I.